let's let's discuss basic structures, the sets, functions, sequences, sums, and matrices. Much of the discrete mathematics is devoted to the study of discrete structures used to represent discrete objects. Many important discrete structures are built using sets, which are the collections of objects. Among the discrete structures built from sets are combinations, unordered collections of objects used extensively in counting. You have the relations, the sets of ordered pairs that represents relationship between objects, graph, sets of vertices and edges that connects vertices, and finite state machines used to model computing machines. So in this discussion, we are going to discuss the fundamental discrete structures on which all other discrete structures are built, namely the set. Okay, sets are used to group objects together. Often, not but not always, the objects in the set have similar properties. For instance, all the students who are currently enrolled in this school make up a set. Likewise, all the students currently taking the course in discrete mathematics at any school make up a set. Okay, so in addition, those students enrolled in the school who are taking a course in discrete mathematics from a set that can be obtained by taking the elements common to both two collections. So the language of set is a means to study such collections in an organized fashion. We now let's have the definition of sets. Okay, take note that the sets are then introduced to you when you were still in the basic education, which is the high school. So let's have sets. So this is the definition. A set is an ordered a set is an ordered collection of objects called elements or members of the set. A set is said to contain its element. We write this symbol, okay, this one, okay, which denotes that A is an element of a set A. So the notation A, okay, you have this one, this notation, okay, denotes that A is not an element of set A. Okay, so it is common for sets to be denoted using uppercase letter. Lowercase letter are usually used to denote elements of a set. So there are several ways to describe a set. You could have the uh, you can have list all the members of the set when it is possible. So we use the notation where all members of the set are listed between braces. So, for example, when you say represent uh, the elements A, B, C, and D in the in a set, you could write this one as you have okay the brace. So you have A, B, C, and D, and then close it again with a brace. Okay, so this method of listing the elements of this set is called roster method. Okay, so for example, a set V of all the vowels in English alphabet. So this can be written, okay, let's say set V, okay, this using method, you could have set of A, E, I, O, and U. So this would be our set V. Okay. So let's have another example. A set O of odd positive integers less than 10. So you could have okay O okay and then equals you have open a brace and then you have 1, 3, 5, 7, and 9. Okay. So let's have this one. Okay, a set of odd positive integers less than 10. Sometimes the roster method is used to describe a set without listing all its members. Okay, uh, let's say some members of the sets are listed, and then ellipses, okay, are used when the general pattern of the elements is obvious. So usually that is uh, written, for example, we have this one, a set of odd positive integers less than 10, and then uh, if ever that there are many elements within the set, and then you use roster method. Okay, for example, let's say this is uh, let's say less than 100. Let's just say this is less than 100. So you could have uh, O is equal to set of positive integers less than 100. Let's say that one. So you have uh, 1, 3, 5, then ellipses, comma, then 99. Because it is very inconvenient that we are going to list all the numbers from 1 to 99, which are all odd numbers less than 100. Okay. However, you could also have another way of writing, okay, the set, not in listing the members. We have the what we call as set builder notation. Okay, we characterize all those elements in the set by stating the property or properties they must have to be the member. So for this example, let's say a positive odd integers less than 10. So you could have 0, not 0, O, okay, and then you have equal sign, okay, open the bracket, then you have x, such that the x, okay, is an odd integers less than 10. Okay, let's have this one to answer this question. Okay, this is set builder notation. Or you could have another way of describing the property of the numbers being described in the problem. So you could have O is equal to a set of x element of the integers which are all positive, okay, which which is the x is odd and the x should be less than 10. This one, okay, the upper one can be read as a set of x such that x is an odd integers less than 10. And then here, you could have the set of x element of positive integers such that x is odd and x is less than 10. So these two, okay, okay, these two ways, okay, are the same. They mean the same thing. Okay. Now let's have sets. Okay. By the way, before I forget, aside from a set builder notation, we could also have intervals. Okay. In your basic education, I guess, and I also believe that the intervals for real numbers was then given to you. Say you could have. Let's go back to the previous one. Okay. You could have this symbol. Okay. This is uh, these symbols implies that the elements here are x such that x is less than or equal to a, but greater than or equal to a, but less than or equal to b. So which is this called closed interval. And then you could have this one. So this means that the elements of these sets would be a set of x such that our x is greater than a but less than b, which is called an open interval. And then we have a half open interval. You could have this one. So this means that you have the elements, okay, of x such that the x is greater than or equal to a but less than b. Then we have also this symbol or this interval, okay, which implies that these would be the set of elements of x such that our x should be greater than a but less than or equal to b. So these are half open intervals. Okay. Because many mathematical statements asserts that two different specified collections of objects are really the same set, we need to understand what it means for two sets to be equal. So the two sets are equal if and only if they have the same elements. Therefore, if A and B are sets, then A and B are equal if and only if there's for all x, okay, where x is element of a rather is also an element of b. So we could write that a equals b if a and b are equal sets. So let's have this one. Uh, the set 1, 3, 5 and 3, 5, 1 are equal because they have the same elements. Note that the order in which the elements of the sets are listed does not matter. Note that it does not matter if an element of a set is listed more than once. So if you have 1, 3, 3, 3, 5, 5, 5, 5, is the same as a set 1, 3, 5 because they have the same elements. So we have this one. There is a special set that has no element. So this set is called empty set or null set, and it is denoted with this symbol. Okay, empty set can um, also be denoted by this one. You have two braces with no elements inside. Okay, so um, e often a set of elements with certain properties turns out to be a null set. For instance, the set of all positive integers that are greater than their squares is actually an empty set. So, a set with a single element is called singleton set. A common error is to confuse the empty set with the set with a set with an empty set. Okay, so um, the single element of a set with an empty set is an empty set itself. A useful analogy for remembering this difference is to think a folder of a computer file system. The empty set can be thought of an empty folder, and the set containing of just the empty set can be thought of as a folder with exactly one folder inside, namely the empty folder. Okay, so Venn diagrams. So sets can be represented graphically using Venn diagrams, okay, which is named after English mathematician uh, John Venn, okay, who introduced this in 1881. The Venn diagrams in Venn diagrams rather, the universal set U, which contains all the objects under consideration, is represented by a rectangle. Okay, note that the universal set varies depending on which objects are of interest. So inside this rectangle, circles or other geometrical figures are used to represent the set. Sometimes points are used to represent the particular element of a set. So Venn diagrams are often used to indicate the relationship between sets. Okay, so let's have this one. Draw a Venn diagram represents V, the set of vowels in the English alphabet. So in this case, we draw a rectangle to indicate a universal set U. So in this case, you have a rectangle, and then let's say this is our universal set U. And then we draw a circle inside the rectangle, and then we may represent the letters with points. So let's say this is our A, this is our E, this is our I, this is our uh, O, and let's say this is our U. And this set is set V. So this is our Venn diagram. Okay. So subsets. Uh, it is common to encounter a situation where the elements of one set are also the elements of the second set. Okay, so we now introduce some terminologies and notation to express such relationship between sets. So we have a set A is a subset of set B if and only if every elements of A is also elements of B. We use the notation A with this symbol, okay, with that symbol to indicate that A is a subset of B. So we could have uh, a set A is a subset of set B if and only if you have biconditional. Okay, if and only if the quantification, okay, you have for all x, okay, in which the x is element of A implies the x elements of B. So that is our explanation in this case. Okay, it must be for all x, such as the x is element of B implies also that x is element of B, which is it should be true. So note that to show that A is not a subset of B, we need only one element x in A with x not element in B. Okay, such an x is a counterexample to the claim that x elements of A implies x elements of B. So we have these useful rules for determining whether one set is a subset of another. We have this one, you already learned this one in your, I believe, grade 7. Okay, showing that A is a subset of B. So we have to show that A is a subset of B. We have to show that if X belongs to A, then X also belongs to B. So when we are going to show that A is not a subset of B, okay, then you could have uh, A is not a subset of B if there is even a single X that is element of A such that X is not an element of B. Okay, so let's have this one. Okay, the set of all odd positive integers less than 10 is a subset of the set of all positive integers less than 10. The set of rational numbers is a subset of the set of real numbers. And you have the set of all computer science major at your class or in the school is a subset of all the sets of the students in your school. And the set of people in China is a subset, okay, is a subset of the set of all people in China. So that is, it is a subset of itself. So each of these facts shows immediately by noting that an element that belongs to the first set in each pair is set also belongs to the second set in that pair. Okay. So let's have this one. The set of integers with squares less than 100 is not a subset of the of the non-negative integers, because negative one, okay, is in the former set. So you have as a you have as uh, the square of negative 1 is less than 100, but not the letter set. The set of people who have taken discrete mathematics at your school is not a subset of all of the sets of all computer science majors in your school. If there is at least one student who has taken the discrete mathematics, okay, uh, who is not a computer science major, okay. So this theorem shows that every non-empty set S is guaranteed to have at least two subsets, the empty set and the set S itself. That is, an empty set is a subset of S, and the set S is a subset to itself. Okay, so let's have the size of a set. Before I forget, so uh, when we wish to emphasize, okay, let's go back to the previous slide. Okay, when we wish to emphasize that, let's say a set A is a subset of set B, but A is not equal to B, we write, you could have A and the symbol B, which can be read as A is a proper subset of B. Okay, for A is a proper subset of B to be true. It must be the case that you have the A is a subset of B, and there must exist an element X. Okay, there must be exist an element X. Okay, uh, in B that is not an element, okay, that is not an element of set A. Okay, so that is A is a proper subset of B if and only if. So you could have, okay, if and only if, okay, there exists an X, okay, you have X is an element of A, okay, which is also an element of B, then there exists an X, okay, where X is element of B and X is not an element of A. Okay. Oops. So you have the size of a set. A set are used extensively in counting problems, and for such applications, we need to discuss the size of the set. So let S be a set. If there are exactly n distinct elements in S, where n is a non-negative integer, we say that S is a finite set, and that n is the cardinality of S. The cardinality of S is denoted by you have the absolute value of S. Okay, so a set is said to be infinite if it's not finite. Okay, so quite simple. So let's have power sets. So many problems involve testing all combinations of elements of a set to see if they satisfy some property. So to consider all such combinations of elements of a set S, we build a new set that has as its members of all subsets of S. So we have the power set. So a given a given a set S, the power set of S is the set of all subsets of the set S. The power set of S is denoted by this one. You have the P of S. Okay. So let's have this example. What is the power set of the set 0, 1, and 2? Now take note that when we say power set, it must be the set containing all the subsets of the set 0, 1, 2. So in this case, you have okay, the power subset of our set, which is 0, 1, 2. Oh, okay. Should contain the elements. Okay, you have the empty, then you have the element of 0, the set containing the element of, okay, let me change, the set containing 1, the set containing 2, then you have the set containing 0, 1, then you have the set containing 0, 2, and then the set contains 1, 2, and then you have the set which contains the set itself. Okay, so all in all, you have you have the empty set, the 0, 1, 2, 0, 1, 0, 2, 1, 2, 0, 1, 2. So you have 8 elements. So note that empty set and the set itself are members of this set of subsets. Okay, so let's have the Cartesian product. So the order of elements in the collection is often important because sets are unordered. A different structure is need to represent the ordered collection, and that is provided by the ordered n-tuples. So we have this definition. Okay, the ordered n-tuples, you have a sub 1, a sub 2 up to a sub n, is the ordered collection that has a sub 1, this must be a sub 1, as its first element, a sub 2 as its second element, and up to a sub n, which is the nth element. So we say that two ordered n-tuples are equal if and only if each corresponding pair of their elements is equal. In other words, if you have set a sub 1, a sub 2 up to a sub n is equal to the set b sub 1, b sub 2 to b sub n, if and only if our a sub I is equal to b sub I for our I would be from 1 to n. In particular, ordered two tuples, which is called ordered pairs. Okay, so the ordered pairs, let's say AB and CD are equal if and only if A is equal to C and B is equal to D. Note that the ordered pair AB and the ordered pair BA are not equal unless A and B are equal. Okay, so we have this one. Let set A and B are sets. Okay, the Cartesian product of A and B, denoted by A by B, is the set of all ordered pairs A, B, where A is element of set A and B is element of set B. Hence, A by B is equal to the ordered pair AB, such that the A is element of set A and B is element of set B. Okay, so let's have this example. What is the Cartesian product of A? Set A has an element of 1, 2, and set B has an element of A, B, and C. Okay, so to show that the Cartesian product B, uh, B by A, by the way, to show that the Cartesian product A by B, we have in this case our A by B, okay, should be equal to the product of the ordered pair 1 A, ordered pair 1 B, ordered pair 1 C, ordered pair 2A, ordered pair 2B, ordered pair 2C. So that is our the Cartesian product of A by B. Okay, so we have this one. The Cartesian product of set A sub 1, A sub 2 up to A sub n, denoted by set A sub 1 by A sub 2 by by so on up to A sub n, is a set of ordered n tuples with the element A sub 1, A sub 2 up to A sub n, where A sub I belongs to the set A sub I for I is equal to 1 or 2 up to n. In other words, the sets A by 1, A sub 1 by A sub 2 by so on up to A sub n is an element of the you have A sub 1, A sub 2 up to A sub n, where A sub I is element of of set A sub I for I is equal to 1, 2 up to n. So let's have this example. What is the Cartesian product A by B by C, where A is equal to 0, 1, B is 1, 2, and C is 0, 1, 2. So in this solution, okay, in this equation, the Cartesian product of A by B by C consists of all ordered triples A, B, C, where A is element of set A and B is element of set B and C is element of set C. So you could have uh, A by B by C. Okay, so in this case, you could have triples. Okay, so you have the triples of 0, 1, 0. You have 0, 1, 1. Then you have 0, 1, 2. Then you have 0, 2, 0. Then you have the triples of 0, 2, 2. Then you have 1, 1, 0. Then you have 1, 1, 1. Then you have 1, 1, 2. Then you have 1, 1, 2. You have 1, 2, 0. You have 1, 2, 1. And then you have 1, 2, 2. Okay. And before you forget, you have 0 to 1. Okay. So note that when set A, B, and C are the set, then you have this one. You have to take note that you have if A by B, okay, by C, okay, is not the same. Okay, if you have A by B by C. Okay, so you have to take note of that. And then if you have a exponent, let's say A squared, that implies that you have uh, A by A. Okay, and if you have A cube, then that implies A by A by A. Okay, so that's it. Okay, so you have this one. Suppose that uh, the set A is equal to 1, 2. What is A squared? So in this case, our A squared, okay, you have the elements contains ordered pair. You have 1, 1, you have 1, 2, you have 2, 1, you have 2, 2. Okay, so that's our A squared. So a subset R of the Cartesian product A by B is called a relation from set A to the set B. The elements of R are ordered pairs where the first element belongs to A and the second to B. So let's have this one. What are the ordered pairs in the less than or equal to relation, which contains ordered pair AB if A is less than or equal to B and uh, on the set 0, 1, 2, and 3. Okay, so the ordered pair, for our solution, the ordered pair, you have A, B. Okay, belongs to R. So you could, it should have belongs to our R if and only if, okay, both A and B, it should have the A and B should belong to the set 0, 1, 2, 3. And then you have A less than B. So consequently, the ordered pairs of R, okay, so the ordered pairs of R would be, you have uh, 0, 0, you have 0, 1, you have 0, 2, you have 0, 3, okay, and then you have 1, 1, and then you have 1, 2, you have 1, 3, 2, 2, 2, 3, and you have 3, 3. Okay, so in this case, you have this one. Oops. Okay. So let's have using set notation with quantifiers. Sometimes we restrict the domain of a quantified statement explicitly by making use of particular notation. For example, we have for all x element of S in the P of x denotes the universal quantification of P of x over all elements in the set S. In other words, for all x elements of S, okay, of P of x is a shorthand for all x, okay, where x is element of S implies P of x. Similarly, there exists x, okay, elements of S of P of x denotes the existential quantification of P of x over all elements in S. That is, there exists X elements of S of P of X is the shorthand for there exists X such in which X is element of S and P of X. Okay. Okay, let's have this. What do the elements for all X elements of R where x squared is greater than or equal to 0 and there exists X element of Z where x squared is equal to 1 mean? Now, to solve this one, take note that this statement, okay, this statement states that for every real number x, x squared is greater than or equal to 0. So this statement can be expressed as the square of every real number is a non-negative. Okay, this is a true statement. Okay, the statement, this statement, okay, states that there exists an integer x such that x squared is equal to 1. This statement can be expressed as there is an integer whose square is 1. This is also a true statement because x equals 1 such that an integer, okay, as as is negative 1. Okay, so that means that uh, all these statements are true. Okay, so let's write this one. So you have for all x element in R, okay, which our x squared is greater than or equal to 0, okay, which means that for every element of x, okay, for every element of x which is real numbers, which is, okay, real number, okay, real number x, our x squared is greater than or equal to 0. So this means, because we have this one, this means that the square of every real number is non-negative. And then if you have this one, there exists x element of the integer, okay, which is x squared is equal to 1. This means that there exists an integer x such that x squared is equal to 1. So this means, okay, there uh, is an integer whose square is 1. Okay, so let's have truth set and quantifiers. We will now tie together the concept from the set theory and the predicate uh, logic. Given a predicate P and a domain D, we define the true set of P to be the set of elements X in that set D, which is the domain for which the P of X is true. The set of P of X is denoted by the elements of X elements of D such that P of X. Okay, so we have this one. What are the truth set of the predicates P of X, Q of X, and R of X, where the domains is the set of integers and P of X is the absolute value of X, which is equal to 1, and Q of X is X squared equals 2, and R of X is equal to the absolute value of X is X. So for our solution, the truth set of P, okay, which you have our set P, you have the element of X, set of X elements of the integers such that the absolute value of X is equal to 1. Okay, is the set of integers for which the absolute value of X is 1, because the absolute value of X is 1 when X is equal to 1 or X is equal to negative 1. And for no other integers x, we see that the truth set of P is, in this case, our truth set of P would be, you have negative 1 and 1. Okay, for the truth set of Q, you have elements, you have the x elements of our Z, okay, integers, such that our x, the square root of x, is equal to 2. Okay, this is 2. Um, you have the set of integers for which x squared is equal to 2. This is empty set because there are no integers x for which x squared is equal to 2. Therefore, our truth value for our q is empty set. Okay. For the truth set of R, you have uh, a set of x elements of z such that the absolute value of x is equal to x. Okay, so this means that it is a set of integers for which the absolute value of x is x, because absolute value of x is x if and only if x is greater than 0. It follows that the truth set of R is all natural number, the set of non-negative integers. So for our R, the truth value would be all natural numbers, the non-negative integers. So note that uh, for all x of p of x is true over the domain U if and only if the truth set of p is the set of U. Okay, likewise, there exists x in p of x is true over the domain U if and only if the truth set of P is non-negative. So that ends my presentation.